Hey there guys, and welcome back for another presentation, this one on California's climate and weather. Now, this kind of gets broken apart in a bunch of different type of slides. I've got some additional videos on YouTube that explain like the average types of, the difference between weather and climate, the average types that we perceive throughout the US and in California. But this one in particular is just going to focus on a couple main aspects of just California's climate and really what makes it such a, desirable place for all of us to live in. So let's start off with this. Well, what is climate? Well, very quickly, climate is kind of the long-term average weather, traditionally over a 30-year time span, meaning I think of it like a generalization. So you can generalize, using your life experience, how hot is summer where you live? If you live in Las Vegas, what is the general consensus, right? So in the classes I often say, like, imagine that I'm going to give you a free all expense paid trip to Las Vegas in July, but now it's October or whatever month it is. So it's months away, but you have to pack for it now. Do you think off of generalizations of long-term known knowledge that you could predict or at least have an idea as to what July would feel like in Las Vegas? And the answer is yes, you could. That being said, some of the variables that are collected in understanding climate is the day-to-day weather stuff, such as temperature, humidity, pressure, the wind variances, so what type of wind direction, how strong is that velocity, and then lastly, we'll look at precipitation. So, again, climate is that long-term. Weather is the day-to-day, right? So today's weather is this. Tomorrow's weather is that, which is kind of like that part to whole. Climate is the generalization of taking, and say, as an example, I'm recording this video on a Monday. So that means if I were to look at every Monday on this date over the last 30 years and put it like in Excel and then do like an average, what is that number? What's going to be the high temperature, the low temperature, the average temperature, what's the humidity, and so on and so forth. So what does it mean when scientists say that climate is changing? So like we have some really crazy weather today. We can't just say, oh, wow, it's climate change, right? Climate change means that we have seen a progressional change in climate patterns over a 30-year span. So when scientists are saying that we're experiencing climate change, that means that we have seen a difference in the last 30 years. Not just today, not just yesterday, not just tomorrow. 30 years of data, we have progressively seen changes. So that means. So when people are like, wow, it's really hot today and being cold the next day, ooh, that climate change. So no, that's called extreme weather, which can be part of a grander scheme, a grander idea or collective piece of information, but that's not what that means. So that being said, how do we look at climate? Well, there's lots of different ways. This is one that I use the most, the Koppen climate classification, which is essentially how do we evaluate an area and give it a code. Now this works really well around the world because it's used that way, but it's really difficult to use in California. Because if you think about it, if you have friends that live throughout the state of California and you call your friend up in San Francisco and ask them what the weather's like for them today, it'll be very different than the weather you're experiencing in Southern California. And then if you call your other friend who lives in San Diego, that can be completely different weather as well. So we can't generalize a type of climate for all of California. Some states you can. Some states you can just give it a code and say this is what the average climate patterns are, but California's a little more complex because we're so long, right? We cover a tremendous amount of latitude. So that's why we can have, snow in one area, rain in the other, and drought in the last. It can be very diverse. So the way this is done is traditionally looking at a 3-letter code. The first letter that will give areas is really kind of describing like the biome in that sense. Like this is a tropical area. Which means it's really moist. This is an arid area, which means that evaporation exceeds precipitation, or it's temperate, or it's going to be continental cold. And the one letter that's not on here is H, which is highlands, which is like super high mountains. And then we can start giving these other things, these other codes, letters. So the first letter is kind of describing the general area. The next letter describes the amount of precipitation, and the last letter describes the average temperature. So this takes, essentially, if you kind of think about it, this is talking about vegetation in a sense. This is talking about just precipitation, and then this last letter is talking about temperature. So as an example, Uh, Most of where I live is considered a CSA. So we would be a temperate region with very dry summers and very hot summers as well. Yeah, that doesn't mean that we're desert, right? Because desert doesn't really necessarily mean that it has to be hot. It just means that we're very dry. We are dry, but not dry enough to be arid, which is kind of interesting. So what they do is we have this little chart giving all kinds of different values. You have semi-arid, you've got low arid, you've got Mediterranean, which is a CSA, which is why we are able to grow so many great things here in Santa Clarita. Cool continental dry, cold winters in highlands and mountains. So how does this look on a bigger piece? Well, I can actually pull up a map that shows the different areas with this. So like I said, Santa Clarita, which is around this area right here, is best identified as a CSA, Mediterranean hot summer. We have areas that are closer towards the beach, which are CSBs, which are Mediterranean cool summers, like Ventura, right? We can see that there's also Mediterranean summer fogs. We can see that there's definitely areas that are arid in the valleys and Mojave. We can see areas that are very, very hot, which is part of Death Valley region. So we start to see these patterns. Now, looking at just the climate patterns and then looking at a map of California, this is a raised relief in a sense, right? Because it's showing a relief with the mountain ranges. Here you have the Sierra Nevada, so on and so forth. You have some of the Klamath Coast, again, the Great Valley, Central Basin. But what we're able to see is, if you kind of visualize looking at this diagram in this map, is that are the relationships with climate as well as relationships within the topography? And the answer is, well, yes, you will find. You will find that, valleys are traditionally drier. You will see that on the western side of the margin of these areas will have the rain shadow effect. So it's going to be moister and greener on this area, but more dry on the other side of the Sierra. Because as those clouds come off the Pacific Ocean, work their way across the valley, and go up the Sierra, they begin to then release some of that moisture. And then when those clouds go over the Sierra into the valley, they're significantly drier. So places such as Death Valley, that's not just in the rain shadow. That's in the rain shadow of a rain shadow of a rain shadow. So, by the time that cloud gets all the way over there, there's not a whole lot left. I have other videos that explain clouds and moisture and stuff like that. If you want to know more, you should certainly check them out. But really the idea is I compare clouds to sponges. Is that they're made of, a sponge is moist. You open up a brand new sponge and it has moisture in it, right? And it can be completely laden or saturated, but it will still hold that moisture. So if you have a very moist sponge coming off of the ocean, you slowly squeeze it every time you get closer to Death Valley. You squeeze it as you go higher up the mountains, right? Because you go up the mountains, lower pressure, and you're also going to be cooler, and it's going to be able to condense. By the time you squeeze that 3 times to Death Valley, the sponge will be damp, but there's not enough moisture to actually cause any droplets to occur. And that's why Death Valley is arguably the hottest and one of the driest places on Earth, which is pretty cool. So this is kind of an interesting way to put that together. Again, like I said, most states you can almost give them just one code, but California is so diverse, because we have such a really a dramatic change in our topography, and we have coastal regions. We've got highlands, up in the looking up in the Sierra Pack up in here. There's just so many wonderful things that California has to offer. It becomes very challenging to just give us a code, and that's why you can take climate, both looking at weather pieces and look at maybe at even politics. That's why there's always been conversation of splitting California up into smaller states, because it's very difficult for us to understand the differences. Looking at Southern California down here being very dry, and areas up in Northern California that have a tremendous amount of precipitation in relation. Then the Central Valley, which is the San Joaquin, which is known for a lot of our agriculture and livestock, that we take precedence of water resources, so we get the water instead of them. And it's like, well, but we don't, we live in an arid area in a sense. So anyway, very interesting things to think about. I chose this map. There's actually an article shared in Canvas about this. I just think this is really interesting. Now, again, this is not really in. This isn't a they're trying to depict it in a singular line. I don't agree with it being that singular, because San Francisco is in a very different spot than Death Valley. But they're just trying to give an example of, like, if you could draw some weird line across the width of California, starting at San Francisco being 0 feet at sea elevation and going all the way to Death Valley, and all of the terrain that you would go throughout is really, really dramatic. So you think about it. This is why we're able to go surfing and snowboarding in the same day if you wanted. So we're looking at San Francisco. We can get into the Diablo Range, the San Joaquin Valley. Then you can move up to the Sierra foothills. We get into the mountain range, the highlands. We can look at Owens Lake, which is other conversations we'll have throughout these videos. Then we go over that mountain range into the Panamint Valley. Then we go over that again and go actually below sea level. Death Valley down in Badwater Basin is actually negative 282 feet below sea level, meaning that if you were standing at Badwater Basin, you would technically, and there weren't mountains protecting that area, you would technically be under the ocean by almost 300 feet, right? That's pretty intense. That being said, that's why some of the hottest recorded temperatures have been seen there, and we'll talk a little bit more about that in a moment. So this is trying to put it in perspective that, just saying that we have a little bit of everything in California, which is really, again, exciting. You think about it. We're able to grow everything from avocados to bananas to berries, flowers, I mean, everything in between. We're able to do, and we'll talk more about agriculture as well in additional videos, but just think about how diverse our landscape is. And why is that? Well, obviously soil science, when we study about that later, has a lot to do with it, but also our climate is a huge attribute to that. If we didn't have this array, we wouldn't be able to provide the diversity in which we have. Moving forward, well, what about climate change? How do we observe climate change? Well, there's lots of different ways. We are observing it through agriculture. We're observing it through water resources, glacial melt, extreme fires. You might notice that my voice is a little crackly, and that is because we have, I think, just within like 100-mile radius of where I live, I think there's 5 major, huge fires within my area. So the air quality is pretty poor. We've been seeing fluctuations of extreme heat. We're starting to see a decline in sea life. We can also observe sea level rise in certain areas, and we're also seeing ocean ocean acidification. That, in a sense, that the pH level of our oceans are changing, and then as a result of that, can affect the sea life and so on and so forth. So I know that the imagery is very small here, but it says, I want to read the text. From the Sierra snowpack to sea levels along the California coast, climate change is already having a significant impact on our environment. The new Indicators of Climate Change report track 36 indicators of change across the state. This infographic presents some of the examples of what those indicators can be. So again, think about how, as an example, agriculture changes. That's one that I'm very passionate about because I myself grow. I always have a garden. I have a huge succulent garden, and I've got also produce. And I also I'm surrounded by a lot of agriculture right now. The new one is avocados, which is great. But it says that when winter chill periods are necessary for the production of a lot of fruits, specifically looking at citrus, they actually need like a freeze to try to, that does something internally in that plant to produce it. But if we have continued warming, we're not going to have that appropriate freeze during the winter that kind of sets off and kind of resets the time in those fruits to when to bloom in spring. So they can either bloom too early or too late. Other things that we observe is that if we have these really intense heat waves and flares, that a lot of vegetation cannot sustain that heat. And as an example, I'll use tomatoes as an example. Tomatoes grow very well in Southern California, but when we have excessive days of 110 plus degrees, the leaves can't do it. The plants, what they'll do is it's called transpiration, where they essentially sweat like humans do. It pushes out excess water to try to cool the plant down, right? But in doing so, if it's a really hot day, that it pushes out that excessive water, and then that water can actually act as a magnifier and will start to burn your plants. So it's kind of like the plant's trying to save itself, but it's just too hot in that sense. And so when we start seeing this occurring in certain places, we have to find ways to combat it. And an often way that it's done, like with avocados, is they're actually just painting the whole trees. They're painting them white with a latex paint base. It's kind of like a sunblock, but that's not a natural thing. Plants did not have latex paint on top of them to protect them. So we're starting to see a lot of changes and adaptations that need to be done in order for the survival of a lot of our agriculture and for really our purposes as an industry. Another thing that we see here is extreme heat. So the frequency and intensity of heat waves have increased statewide since 1950, jeopardizing public health and agriculture. So we have to now have safe spaces throughout the state of California for excessive heat waves. Um, it'll talk about in a moment, but we just set another record in California and this is now 2020. We set another temperature record, which is, it's cool to set records, but it's also terrifying. And I'll talk more about that too. So anyway, this is just a great example of like when looking at long-term stuff, like what's changing, what are we not able to adapt to? We constantly in Southern California deal with drought. I mean, the whole state deals with drought, as a whole piece. And we'll talk more about water resources in the Los Angeles and California aqueduct and how we move water from areas that have excess water to areas that, the haves versus the have-nots. But as we continue to see a larger difference in that amount of precipitation that the state accrues, who gets the water? Who gets to have that privilege? Who's going to pay the most for it? I mean, people don't often realize that some of the water that California consumes is not even from California. We're actually buying it from the surrounding states at a premium, meaning that we're paying more for it than it's worth. And that's another conversation to have about within climate change. Now, when I also mention climate, there's these things called climate graphs or climographs, and what they do is they take a tremendous amount of data. Again, climate, so 30 years plus of data, and they put it onto a graph to understand averages. So this is a climograph of Santa Clarita, which is close to where I live. And so what it's able to do is it first shows us precipitation. So these little, in this, for me, it's kind of like a mauve or a light purple. This is the measured precipitation on average, is these squares, and then the blue line that kind of transverses across the graph represents the average degrees in Fahrenheit. Again, this takes the high, the low, and creates an average, right? So, as an example, last night, the high where I live, because this is summer, was 116, and the low last night was like 94. So it's going to have to take the average of those two. This is obviously an anomaly. This is extreme weather, not something that's very common this late in the year, but nonetheless, it occurs. So as an example, in January, the average is about 49 degrees, and we see on average we get about 2.6 inches of rain. This is being recorded in September, so we see that we on average get about 0.2 inches of rain, which is usually from a summer storm, and we see that the average temperature is probably about 72 degrees. Again, that's taking the high and the low and averaging across the board. And we see on average Santa Clarita has received 13.9 inches of rain per year, and the average temperature throughout the entire year is 60 degrees Fahrenheit. Again, this is a generalization, right? Obviously, like as I said yesterday, this is September, we exceeded this number. So it's taking the averages of 30 years. But as we continue to collect data and we have to make continual changes to this, that's what we're observing as climate change. It's like, wow, this graph, taking all that data from these last 30 years and the next years and adding that and so on and so forth, we start to see that there's slow changes. We start to see that this curve is getting higher and that we're not starting off this cool. That is going to be observable and interpretable change. Here's another location. I picked Death Valley. As you can see, on average, they get about 2 inches of rain per year. That being said, the rate of evaporation is a ridiculous amount compared to that. We're looking at, off the top of my head, I don't remember. I think it was over 100 inches of rain per year could evaporate in Death Valley. Like if you had a lake that was over 100 inches deep, it would evaporate completely in the course of a year. So obviously their rate of evaporation exceeds their precipitation. You see they get very little rain, and look, it's off the graph on average. During the summer, we're looking over 100 degrees. On average, it usually doesn't even go below 100 degrees at night, so it kind of stays around there. Luckily, we have this dry heat that we in California love to talk about, which I agree with. I do not do well with humidity. Dry heat is much better for me. But look at how intense this graph is. So pretty impressive. Death Valley. Last one I have is Sacramento. As you can see, they get on average 17 inches of rain per year. Much more mild. Again, drier in the summers. Is there a correlation with when we have more heat versus less rain? I mean, I see that curve. Like this goes low, high, and low. This is high, low, and high. I certainly see that there are patterns and correlations with temperature and precipitation. But this is Sacramento. Just again, I picked 3 different spots within the state to show you different climographs. So since we've kind of talked about this extreme weather and anomalies, let me give you an example. I'll talk more about it in another video when looking at water resources, but this has always interested me. This is the Los Angeles flood of 1938. It's a huge flood that occurred. This is not the first and it wasn't the last, but this was the flood in which the Army Corps of Engineers got involved in the state of California and then created the channelized Los Angeles River, which was a necessity at that point to prevent this from occurring. I believe that we're looking over at Victory Boulevard. This is the overflow of the Los Angeles River covering all the roads and the neighborhoods. So between February 27th and March 3rd, a storm came from out the Pacific, went over through Los Angeles, went up towards the San Gabriel Mountains, and within those several days rained about 40 inches of water. That's about 3 feet of rain. So if you had a rain gauge that's a foot tall, you would have filled 3 of those. Now, that's within that area. Then you have to take in consideration runoff, the size of the area. So that's why, even though it only rained 3 feet, we found in certain areas, such in Orange County, that were submerged between 6 and 8 feet of standing water, which means that by the end of that weekend, most of those areas had over 6 feet of standing water. So Riverside County, with a population of about 200, was completely swept away. I have additional videos. We'll talk more about this later in the semester, but I wanted to give an example of extreme weather. It does occur. In fact, since I'm mentioning extreme weather and we've got all these fires, another fun thing to look up would be the pyrocumulus. That's a special type of storm cloud that occurs because of fires. It's a beautiful, magnificent cloud, but it can also produce lightning and stuff like that. But anyway, fun fact, I grew up in Baldwin Park, which is out in LA, and the house, the back house that was on the property, had water damage from the 1938 flood. I remember seeing that as a kid, that there was like a weird rim around the perimeter of the building, and the wallpaper and the drywall was kind of destroyed, and that was from the standing water. It was about 3 foot high in that house, which was impressive to say. But we'll talk more about that as well. So since we're talking about weather and extreme weather and stuff like that, let's talk about some records, right? So California has actually the hottest recorded temperature in the world was in Death Valley. It was 134.1 degrees Fahrenheit in 1913. It was so hot that birds were dying in mid-flight, just their hearts were exploding and they just collapsed to the ground. But in 2020, we hit a record in California again. We hit 130 degrees in Death Valley, which was, again, the hottest recorded temperature since 1913. So in 100 years, we hit another record of just, we haven't had another extreme heat like that in Death Valley in 100 years, and we hit it again. Exciting. Terrifying, somewhere in the middle. The coldest temperature recorded in California was in 1937 in a place called Boca, California. It's near Truckee. It was negative 45 degrees Fahrenheit. And the greatest amount of rainfall that had occurred in California within a 24-hour span was 25.83 inches in 1943 in the San Gabriel Mountains. 25 inches in less than 24 hours. That's pretty impressive. So again, this video is really to kind of introduce the fact that we have an incredibly diverse type of weather and climate systems, to also establish the differences between weather and climate, and to also look at how just regionally we're able to observe and interpret weather and climate and its diversity in California. I hope you enjoyed this. Don't forget to like and subscribe the channel to check out the other videos, and we'll talk real soon.